let's talk some about covalent bonding. So covalent bonds are going to be ones where two atoms share one pair of electrons instead of one of the atoms taking the electrons away from the other, which is what was happening in our ionic bonds. Most atoms are attempting to obtain 8 electrons in octet, and so this is why they share. They're sharing so that we can have multiple atoms when there aren't enough electrons managing to reach their octets anyway. Hydrogen is the one exception to this that the main exception we're going to deal with in this class. It's only going to need 2 electrons. There are a couple others that'll come up later, but that's the main one. So one atom is going to use more than one single bond to fulfill its octet in some cases. So sometimes your atom might need 2 more electrons, so it's going to borrow from 2 different partners, or it might take one atom and borrow 2 electrons from it. So what does this look like? Let's take an example of a water molecule. So a water molecule is H2O. And in the next chapter, we'll look at where this drawing comes from. For now, I'm just going to show you how you would arrange it. So water will have one hydrogen atom. There'll be a set of electrons. I'm going to draw this in a different part of the screen so it's easier to see. So we've got hydrogen. We have one pair of electrons. It's sharing with an oxygen atom. There's another pair of electrons it's sharing with a hydrogen atom. And then the oxygen also has some extra electrons here. The idea behind this is each hydrogen had 1 electron to start with, and oxygen had 6. That means between the 3 atoms, there were 8 total electrons. So if we were thinking like an ionic bond, that would only be enough electrons for oxygen to have its full set, whereas the 2 hydrogens would have to be left out with nothing. However, by sharing, it's possible for both hydrogens to get the 2 electrons they want, and for the oxygen to get to its full 8 without anybody having to give up more. So they don't have to create a charged molecule where they're just attracted because one's positive, one's negative. So the electrons that are shared between these, so this electron pair here and this pair here, those are called a bonding pair. They're called a bonding pair because they are shared between 2 atoms. And so they're going to most of the electron density is going to occur between the hydrogen atom and the oxygen atom. We could also have other electrons in this picture, and we know these as lone pairs. So these are going to be electrons. I'm going to put them with boxes instead of circles. These are our electrons that only occur on one atom, rather than being shared between multiple. We can also sometimes call these non-bonding pairs. I'll use the term lone pairs for my stuff, but just so you recognize when you look elsewhere, that you might sometimes see it listed other ways. So like we said on that last slide, sometimes atoms can share more than 2 electrons. So the atoms are going to, in all the molecules we're going to look at, the atoms are going to share their electrons in multiples of 2. But it is possible for atoms to share more than 2. So for example, a double covalent bond is where 2 atoms share a total of 4 electrons. So what does this look like? Let's look at an example of the oxygen molecule. So in the oxygen molecule, each oxygen is going to be sharing 2 bonds, and then it's going to have 2 lone pair setups. This is because the oxygens both together each had 6, so there were 12 total electrons. But both wanted to get 8 total. So if it only shared once, then they would only get to 7 each. So the oxygens share 2 different times, so they end up with 4 electrons being shared between them. We'll also sometimes write it where it's like this, where instead of drawing the dots, we'll draw 2 lines. And then you can draw dots for the electrons here. Or sometimes you'll also see people that will draw lines for the lone pairs as well. These are all 3 possible ways to draw that oxygen atom, and it means the same idea. That the oxygens are sharing 4 total electrons, which is 2 different bonds between the oxygens. We can also have a triple covalent bond where the 2 atoms share 6 total electrons. So let's look at nitrogen as an example of this. If you have 2 nitrogen atoms, they have a total of 10 electrons between them, but they want to still get to 18. To do this, they're able to share 3 sets of electrons and just keep 1 lone pair on each nitrogen. We can also draw that one like this, or like this. And these are all potential ways to draw the atom. You'll notice that this line notation, it can be confusing and look like a letter. So that last notation is not one that I always like doing because it can be confusing, but it's also the fastest to write, so I get why students tend to like that one at times. So we can have single, double, and triple bonds depending on our particular atoms and how many electrons they need. Our next chapter will go into great detail of how do I determine whether it's a single, double, or triple bond. Because so far I have not given you enough information to figure that out. I've only explained that it's possible and showed you some examples about why it happens. But I don't expect yet that you would be able to come up with those drawings by being told, oh, you have two oxygen atoms, connect them. We'll get there though. So, what do we know about covalent bonds that we wanted to remember before we start worrying about this naming stuff? We've got two conceptual things to cover. So unlike ionic bonds, covalent bonds are going to have a direction to them. Because the electrons are shared between the two atoms, most of the electron density is going to occur right between the atoms, rather than being spread out in all directions, like when we talk about electrostatic attractions. What this means is that covalent compounds can have a discrete small number of atoms that make one up, instead of ionic compounds that occur in giant crystal lattices. We talked about how with sodium chloride, for example, you could have a mole worth of atoms, or maybe a tenth of a mole, or a hundredth of a mole. But either way, you were having significantly more than trillions of atoms in your NaCl setup. But if I have a molecule like water, each water molecule has one oxygen connected to two hydrogens. I don't have one oxygen connected in this big long wave. So even though there are a lot of water molecules around each other, they come in discrete little packets of single water molecules. So that's our example, water. So our covalent bonds are also mainly going to be created when two or more non-metals bond together. So ionic was a metal and a non-metal. Covalent is going to be multiple non-metals. While I will mention that you have metallic bonding as well, where two metals bond, that's a different type of bonding, and we're not going to cover metallic bonding in this course. So I'm just going to mention it exists, that yes, if your brain goes, wait, two non-metals is covalent, what's two metallic? I'll mention they exist, but we're not going to cover them in detail in this course. So this last conceptual thing before we get to the actual naming process is this thing we mentioned, diatomic molecules. So what am I talking about here? Some of the atoms in the periodic table, when found in their natural state, occur as two atoms which are covalently bonded together instead of single atoms by themselves. I'm pointing this out independently of a very specific example because it comes up practically in a lot of problem solving. So these are called diatomic molecules, and the ones that you need to know, and you should memorize these, are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And rather than trying to just memorize that as a list, although it works, if you look on your periodic table, hydrogen occurs off by itself, but all the others make an L shape in your non-metals category. So if you look at your periodic table, I think that's the best way to memorize it is, in your periodic table, hydrogen in the upper left is just kind of on its own, and you have to know this one's diatomic. But these other elements occur way at the edge of the periodic table, and they occur in this L shape over here, where you have the noble gases going down, and then to the left of them, you have all of these, like fluorine and chlorine, and they all fit in here, and then you have like oxygen and nitrogen, and I guess I just finished that up, bromine, iodine. So they occur in this shape, and by thinking of it in this shape form, it can help like, oh, I can make this L here of all the ones at the top, starting with nitrogen, going to fluorine, and then going all the way down to iodine. Or you can just memorize the specific ones if you prefer that, whichever way works best for you. So the reason this is relevant is it means if a problem says something like a sample contains 12.5 grams of bromine gas, I'm going to expect you to know that that is Br2 gas and not Br gas. So that's the very practical application of this. 2 chapters from now, we're going to start doing a whole bunch of work with chemical formulas. And so you'll have problems that are like 12.5 grams of bromine gas reacts with so many grams of some other material. How much product do you make? You have to know that that bromine gas is Br2, not Br. So that's how it comes up. So how do we name these things? So molecular compounds are named according to the following rules. You write the name of the element with the smallest group number first. If 2 elements lie in the same group, then write the element with the greatest row number first. And a prefix is given to each element to indicate how many of the atom is present. Note, we'll do some practice with these. I know just reading these can be like, wait, what do you mean? For the first element, if there's only one atom, the prefix mono is omitted. So an example, because I just said a whole bunch of rules, is take CO2. This is something that even if you know no naming rules, you've heard of that as carbon dioxide. You'll notice it's not monocarbon dioxide. So because there's only one carbon, but it's the first atom, we drop the mono. But for the second atom, we're going to keep its prefix of dot because we need that. Just like it would be carbon monoxide if there was one oxygen. Where then with carbon monoxide, you still keep the mono prefix on the second atom, but not on the first. With the other rules, the naming element with the smallest group first, for example, carbon is in an earlier column than oxygen. So we put carbon first in the name, and that's why we do that. So the prefixes are the same ones listed as the hydrate, so if you learn those, you will know them for this as well. The only one that won't come up is hemi, because you're not going to have half an atom in our molecular compound, because they can't have half a carbon here. So we won't have to worry about that one, but all the others will come up. So how do I solve these questions? Let's take an example. What's the name for N2O4? Without worrying, so first we notice it's a nonmetal and a nonmetal. That means this is named with prefixes. So before worrying at the prefixes, I'll just write that it's going to be nitrogen. And then we're going to have, let me check something. Yep. And then we're going to have oxide. You'll notice we're still doing the IDE ending. I should have mentioned that in the last slide. So we still do the IDE like we were doing earlier with the ionic compounds. So the last one gets an IDE ending. So we have nitrogen oxide. But that doesn't tell us how many of each of those there are. It turns out, for example, with nitrogen and oxygen, there are many different combinations. So that's why we're using the prefixes. Technically, there are things like NO2. There's NO3. There's N2O5. There are a number of others, and there's N2O4. There's some other naturally occurring ones as well. So for this reason, we need a way to know how many you have of each atoms. That's why we're going to use prefixes. So 2 is the prefix di. We put di, nitrogen. And then 4 is going to be tetra. So we'll do tetraoxide. So dinitrogen tetroxide. That's what our name is for N2O4. I do think these are some of the easier compounds to name. It's take the 2 atoms, put a prefix in front of both. You won't have any polyatomics with these to worry about. So now, try naming these 3 real quick. Well, it doesn't have to be quick, but pause me and try it before I go over it. Okay, let's review them. So this one, we start with nitrogen. It's the earlier group number. And there's only one of them, but it's the first atom, so we don't have to worry about putting a prefix. We then have 3 iodines, so that's going to be triiodide. Now we'll go to the second one. Again, we have phosphorus. It's in an earlier group, so we put it first. And then we have 5, so we have pentachloride. Now, finally, we have P4S10. So this one, we've got multiples, so we have to put something up front. So 4, again, was tetra, so we have tetraphosphorus, phosphorus, and then we have 10, so we have decaoxide. So we can use as many as 10. P4S10 does exist, so we do use things like nona and deca, so you do have to actually learn all the way up to 10. Now let's try doing the other direction. What are the chemical formulas for dinitrogen pentoxide and sulfur dichloride? So try that out. So now, here, we will get N2, because there's 2 of them, and then pentoxide, so that's 5, so that'll be O5. We then have sulfur dichloride, so sulfur, because it doesn't have a prefix, I'm going to assume there's 1. And then for chlorine, it says di, so there'll be 2. As a final note, with all this compound naming stuff we have to do, the way I'm going to worry about this, usually spelling is not a big deal. Obviously, most times you're taking multiple choice tests, but if you ever have to fill in the blank for something and I manually grade it, what's going to happen is I'm not worried about spelling of things that aren't affecting with the name. For example, if you took the word phosphorus and let's say you forgot this P here, or something like that, I'm not going to make a big deal out of it. That's okay. There's a few things that matter that I do have to grade. 1, if you change the last couple of letters, those are significant. So for example, if you named it instead of pentachloride, you named it pentachlorate, well, chlorate is a different thing. So even though you just changed like 1 or 2 letters, that made a big difference. If you misspell your prefix in such a way that I don't know which one it was, that would be a problem. For example, if you claimed that, oh, I know I wrote tetraiodide, but I really meant triiodide. I just misspelled tri by spelling it tetra. That would be an issue, right? So if you miss 1 or 2 letters, but that means you got the wrong prefix, then we have an issue. I'm not concerned, though, about, oh, wait, for tetra, did I leave the A on or not? Should I do that? I'm not worried about something like that, so it's okay. Or if on the IDE ending, you left an extra letter, like you weren't sure that you had oxygen. And we know, because we practiced with that one a lot, that it's oxide. But let's say you weren't sure about that. You used some atom you never used before, and you thought it was going to be oxygenide for whatever reason. Now, oxygenide is not right, but you wouldn't have a particular reason to know that if it's something you hadn't worked with much. I would give you full credit for oxygenide. We aren't trying to cover that in this class. Now, specifically in this one, please get oxide right. We use oxides a lot, including things like you've just heard of before, like carbon dioxide. But as an example, you know something from, I would not be stressed if you'd put oxygenide, because you got the rules, the idea of IDE, you just didn't know exactly where to do it. Change the ending because it's not something you'd work with a lot, and we have it covered in great detail. Oh, here's how to know which of these it is. So with that finishes up our section on naming compounds. Right? Yes, that's the end of that slide.